Good morning, everybody. So I'm here to talk about this question whether submesoscales exist in the ocean, and if they do, what is it they do in ocean transport? Okay, that's good. And much of this work has been conducted in the context of CART consortium. This is the long name. And we were funded in the aftermath of the BP oil spill in 2010. And this is a very pretty picture of the oil spill. And by looking at this picture, you can actually suspect the answer to the first question is probably yes, because we see a lot of coherent features in the ocean that are on the scale of hundreds of meters to several kilometers, and that's the regime for submesoscales. But first, I would like to start with the big picture, which is a dilemma of oceanic turbulence, which was stated by Jim McWilliams 20 years ago. He started asking these interesting questions, saying that oceans have a very high aspect ratio at the large scales. They're like 1 to 1,000 paper thin, and strongly rotating. So this leads to two-dimensional flows. In 2D, energy cascade is mostly upwards from small scales to large scales, and therefore an interesting question arises in the fact that how can the mesoscale features access dissipation, or do they live forever? Now we can look at satellite images that became available in the 70s, 80s. Now we can get regularly 4 times a day at 1 kilometer resolution. They are not necessarily super informative because, I mean, as George will say, mesoscale structures can also generate a lot of fragmentation, fine scale fragmentation as well. So that's not necessarily mean that you have submesoscale features. And then the other thing for me is that humans have been sailing for ages. We know about waves, winds, tides, Gulf Stream. How is it that we missed a link for so long in the ocean? So this is another way of looking at it, taken from Jim's paper. He's been writing review papers now for the past few years. If you look at scale-dependent things, what's happening in the ocean, we know about mesoscale features that are rotationally controlled, very rapidly rotating, two-dimensional. And then we know about three-dimensional turbulence, okay? And if submesoscales exist, they kind of fall in between and that maybe act as a conduit, as a bridge of energy transfer one way or the other, okay? We don't know that yet all that clearly, okay? And this would put them in terms of non-dimensional parameters at Rossby number of order 1, which means that the flows are kind of weakly controlled by rotation. They're not strongly controlled by rotation, but rotation is in there. So something like hours to days, okay, in terms of time scales, and hundreds of meters to several kilometers. Okay, they are smaller than mesoscales, much larger than three-dimensional turbulence. And the grand challenge is that they've been very, very difficult to observe. Why is that the case? We can observe the mesoscales quite well using satellite technology. These things go around the planet several times a day and resolve more or less. We can debate that. And then three-dimensional turbulence, you can put them in the lab. Many are experts in that. And these scales are kind of awkward in the middle because they are much larger than human size and much larger than ship size. Yet they are very, very fast. Okay, the ship is not a fast thing. Okay, so it takes, the ship will not travel all that long. Yes, if things are changing every hour, you have a trouble to capture that. And so this intermediate regime has been very difficult to capture observationally. So Jim has been pushing for that, Jim McWilliams, and then he had a number of collaborators, and Rafael Ferrari has been the other big force behind this. And then they published a number of very interesting modeling papers 15 years ago. And ONR, Office of Naval Research, bought into this idea that we should look for submesoscales in the ocean because it has actually impacts for naval operations. Fast, strong things, they care about that. So I was part of this team as a modeler at that time. And early in the program, we had very kind of simplistic looking questions. I was very suspicious about these modeling studies for a while because the grid spacings were order 100 meters, and this is the scale of the submesoscale. and they kind of fall in the hydrostatic, non-hydrostatic boundary. That's what Pete was talking about a couple days ago. So is this a real thing? Is this a spurious thing that's happening? Because you have, this is when the non-hydrostatic effects kick in, and you are using a hydrostatic model. And it's never the dissipation errors that matter, because you can always deal with dissipation by eddy viscosity. It's the dispersion errors, because once the wiggles get in the game, they stay there forever. You cannot kill the wiggles with dissipation. So that's why I think Pete's approach, he's obsessed with spectral element modeling, and I was for a while. That's the only way to go. I mean, you can only deal with dispersion errors in high order numerical modeling. Now, even if it's real, then the question is how they can compete, the small wiggles, submesoscales, how they can compete with the large mesoscale eddies. Because the very concept behind LES has been the big eddies control the game, the small eddies kind of ride them, and then you just worry about the big coherent structures that are doing the transport, and you don't worry about the small ones. And that's why LES is much cheaper than DNS. And then the observational people would ask, where do we go? Okay, show me a place in the ocean to go to find the submesoscales. How would they look like? How do we measure them? What is it they do? Okay, so we spent a year and a half talking about these things. Okay, and finally they said, okay, we are just going to go out in the ocean, look for these things. Okay, and the experiment was very extensive in terms of equipment involved. We had 3 ships, okay, operating together. There was a plane used to look at the dye release. There were dye releases made below the mixed layer. There were several drifters, not too many drifters. There were AM apex floats, profiling floats, and all kinds of gliders and all that stuff, okay? So typical, I would say, traditional oceanographic technique. And this is to show you how hard these guys worked. I was not in this cruise, actually. I was doing the modeling before. For about 1 month. Okay, they were really, really, really working hard, trying to sample. Actually, the 3 ships were operating at 3 different grids, and they were just doing, the best, not sleeping at all. I mean, there is no night, day. They don't know. Okay, this is a tracer release from plane doing the tracer operations. And I don't know whether you got the labels here, but there was a big nutting 1, big nutting 2, big nutting 3. Let me do this again. I mean, it's not the first movie I will show, but just want to show you the big nutting, broad. So this shows where the experiment is going. Big nutting A, another big nutting. Okay, so did we find submesoscales in this cruise? No. Okay, even though we wrote a very nice paper, polished things up and all, it was a kind of a failure. Okay, why is that so? There are 3 reasons for it. Okay, the first reason is that we ran some numerical modeling afterwards and showed that actually submesoscales in this region are inside the mixed layer, surface intensified, whereas we were doing sampling just below the mixed layer. Very naive at that time. And then the mixed layer is very, very shallow in the summer, where this experiment was in the summer, 20 meters, because we needed to see the dye from the plane. So we went there at the shallow mixed layer, just below the mixed layer, so that we could see the dye from the plane. The plane has the advantage of sampling the dye very, very fast. As opposed to ship, you don't know anything, you just go around and do that. So the 2 main reasons were we sampled the wrong place, okay, wrong time. Okay, and the third reason probably was that it was really, I mean, it's a bit blunt, but the instrumentation, the measurement techniques were too slow and there was too much aliasing. Okay, you cannot just catch up with these things, as you will see in a moment, with the ships. So we were lost for a while. I mean, people didn't know what to do, but then something very spectacular happened. Okay, just around the same kind of month. The Deepwater Horizon oil spill, as you know, in 2010. And what was special about this experiment was that there was a lot of tracer, much more tracer than we had during the Latmix cruise, which was like a barrel. This thing was millions of barrels, sustained for 3 months. It was like It was actually one of the biggest things that happened in oceanography. I talked to a lot of senior people. They said this was the biggest event that put oceanography into public eye, because people don't know anything about the ocean. And the tracer is at the surface, not at deep, most of the tracer. So what this thing showed was, it was a, oceanographer's dream, even though it was a kind of a bad event, but every day we would get images. I was like working till 3 a.m. every day. You see that this was mentioned before. George worked on it. He has a very nice paper on the tiger tail. But this is the mesoscale feature. Frontal things you can see, Langmuir type of thing. You could see everything all the time. Okay, and then the question became, well, there's so much stuff going on in the ocean that you can clearly see now simultaneously. Okay, what processes matter for transport? All of them. Do mesoscales dominate? What do these guys do? And so on and so. Those are the questions. So when we got funded, we said, okay, why don't we, since this traditional, ship sampling did not work, do the drifters, because drifters do not alias. They just sample the flow field all the time. They're very intuitive to visualize. Transport is a Lagrangian problem. It's not an Eulerian problem. Okay, so people were not buying I was trying to sell this idea during the LATMIX, but there were no buyers. But then we got funded, and I had, I could do my thing, right? So we wanted to look at a statistical measure of dispersion, and one thing that we were, this the first step we wanted to do was to look at a scale-dependent Lagrangian measure of dispersion. And what you do is you essentially release two particles, or drifters, let's say, distance of delta apart, and look at how long it takes for this distance to double. And you plot 1 over tau here. And then you have to do it, of course, for many drifters to get statistical accuracy, and many initial distances, because this actually initial distance measures the effect of each process at that scale. So we have this graph that's 1 over time. It's faster here. And you have essentially very large scales, mesoscales above the radius of deformation, tens of kilometers, and submesoscales going down to, let's say, GPS accuracy. Now, this regime, the mesoscale regime, was kind of known from previous measurements because people have deployed a lot of drifters in the ocean, different cruises over time, and you can actually get these things and put this thing here, and this was Richardson slope. Now, people didn't like to put all drifters on top of one another because they thought this was a waste of resources, so they put something here, the next day 10 kilometers apart, and so on and so forth. So there was no data in this submesoscale regime. And we had two hypotheses. Hypothesis one was mine. I said submesoscales do not matter, so things get faster and faster and faster because I'm coming from LES notion, and it will freeze. Submesoscale will not do any transport. And some people said, well, what if the ocean is a very democratic place, and then everybody has a say, so it keeps going up and up and up. And this thing is actually big. Okay, it's not 2, it's 1,000. It's scale difference. So we actually went out there with the idea of finding this out, this thing, the first cruise. Now, the next question we had was, how many drifters do we need and how do we deploy them? Now, for that, I conducted some larger simulations just to get a feel of how is it to sample a multi-scale flow field and whether we can use drifters to see this, different scales and so on and so forth. And I'll show you the simulation next. But my conclusion was, this is published, at least hundreds of drifters, 100 to 300 drifters. We need 30 days of data, many times the submesoscales, and we got into this mesoscale regime. We also needed very fast transmission, 5 minutes, and accuracy. Okay, we couldn't get away with kilometer accuracy, but we need to have meters accuracy. And then once we had these results, I started calling all the drifter companies. And there was nobody who could give us this 300 drifters in 3 months. We had actually 3 months to conduct the experiments after we got funding. So we actually built the drifters ourselves. First ones were code drifters. This is the simulation on which these results are based. There's a surface front generating, submesoscale. It's a mixed layer instability. It's a small baroclinic eddies. And then there's a deeper front that's going to become unstable in a second. And you will have larger eddies. And then the idea was, like for right now, for instance, you have these two eddies superimposed, and whether you could see these things in the scheme. Okay, you can see the small one and large one. So that thing shows you these coherent structures. Okay, so this is the experiment, the first experiment that we called GLAD, Grand Lagrangian Deployment. At that time, it was the largest synoptic drifter deployment, 300 drifters over 10 days. We chose, of course, the Deepwater Horizon site. We had single ship and just drifters, nothing else. One of the guys said, the chief scientist, you have to make an easy pattern for the ship. S is a good pattern because it's space filling. And we said the S pattern would be 10 kilometers by 10 kilometers. But then we had nodes, okay? Because we wanted to sample all of these things, separation scales, all at the same time. Okay, it was not enough to put some, cluster here, let it evolve. We want to see what's happening at all scales at the same time. So for that, we developed this multi-scale kind of fractal sampling, where the nodes were 2 kilometers apart, and each node has three triplets. The first triplet was 100 meters apart. The second was 500. This was 2 kilometers. The node is 10 kilometers. Then we had different S's 50 kilometers apart. So you could span hundreds of kilometers all the way down to 100 meters simultaneously. And we were very lucky. I mean, I was very skeptical whether this can be done in the field. But we had very good people, in particular, very good students who were very good at sea. So these guys knew how to do these things very, very fast. And this is our ship full of drifters, and we were actually assembling drifters, giving to students, and they were just deploying according to this template. Did it work? So this is the template we wanted to put. This S is 90 drifters altogether. One S pattern is a 90 drifters. And the captain was confused much of the time, but he was like, what are you guys doing? Just go there. 5 hours later, he didn't understand, he gave up, but it was good. So blue are the ones that are deployed, black are the kind of what we wanted to do. We didn't correct for the currents because we didn't know the currents. It's good, okay? This is the whole deployment pattern. We came from Miami and deployed kind of a pre-survey deployment first, and then the ship is refueling. Somehow they need to refuel all the time. I think they were going to New Orleans, but yeah. I was very suspicious of the captain. Of course, this is hurricane season. So we were thinking, what if there's a hurricane? So we came back earlier, but then right after they kind of spread apart, there was a hurricane that passed over our drifters. Drifters survived, very few losses. And somebody got a PhD, actually, one of our students, looking at waves and mixed layers, deepening, and so on and so forth from this drifter dataset. Of course, we had a bunch of models, ARC, coupled models. This is an NRL model. I like that very much because they assimilate all the data they have. And these guys have been doing this for a long time. So they, universities are harder to do that because you need continuity. And NRL is there funded to do this. So they were deploying the synthetic drifters at the same location as our real drifters. What did we find out? So we found out 3 important things. What's the dispersion curve? Is it submesoscale dictating the flow field, or submesoscales have a say? Submesoscales have a say. This is what we found from the drifter observations. This is what the model does. It runs out of steam. Once it gets to the submesoscale regime, it doesn't have the resolution. And it doesn't see that there's a dispersion deficit. If you know the answer, you can easily correct for it, either by high resolution or parameterization, but you need to know what the real ocean is doing. So NRL folks were not super happy about it, but they took it constructive criticism, and they really fixed quite a bit of it. An interesting thing was looking at comparison to altimeter, which is using the geostrophic relationship. And we found huge errors there too, a factor of 20 or something like this. So after this paper was published, I was contacted by NASA people doing the measurements. What's going on here? So we had a meeting with them, and they joined our subsequent cruises to test the sensors. What they do is they fly plane. We have these in-situ observations, and they actually improve their sensors quite a bit. The next sensor didn't work either, but the following sensor, which was not a radar, but Doppler scatterometer, that gave very, very good results. So these things go up to satellite 5 years after they test or something like that. So then we started getting close to the shore, and I actually did not know much about the region at that time, that we started discovering all kinds of freshwater outflows near the coast. Mississippi is not the only one. There's a lot of these tidal inlets and so on and so forth. And the next experiment is the first time we started thinking about aerial measurements, because we were mostly oceanographers, looking down. But the oil is at the surface. So we said, why don't we just we can have observations from planes and helicopters. So we had a little balloon that we bought just before the experiment. I was just flying that and looking at the dye releases we made at the beach. This was mostly a beach experiment. And then I finally rented a helicopter. The university was very alarmed, oh, what are you doing? Anyway, and then we started taking pictures of the dye releases from the helicopter, which was very, very easy and fairly inexpensive. It's not an expensive thing. And very curiously, this dye would never make landfall. Okay, so if you would talk to the people on the beach, how was your experience during the Deepwater Horizon, they would say, oh, it never came there. It was just kind of over there, but it never polluted the beaches. It's very suspicious. And then, at some point, we superimposed all our drifters on a SAR image that became available. It's a synthetic aperture radar. The Americans don't do it, but the Europeans have it. So we had to have a European connection to get that. It's impossible to get it in the US. It's very interesting. And then we found out that all our drifters were released over time are on fronts. And these fronts, most of these fronts were generated through a tidal inlet. The experiment was based here, so we were releasing drifters here. There's this freshwater outflow plume coming out, creating these fronts. They kind of propagate away. And this thing is collecting our drifters. So this is kind of an explanation why this thing was really protecting this area, like a natural boom. And then when I saw that, we just jumped on a small boat and started looking for what is this here? Can I see it physically? And then we immediately found it. Very, very narrow, this wide, okay? Less than a meter wide. One side, there's a lot of these animals. On the other side, it's clear. All our drifters released over the past week were on it. Then, in the second round of our funding, these are 3-year fundings, we were getting more courageous and ambitious. So we said, okay, this drifter thing is kind of working. We still do not quite know what's going on, but let's have more drifters, 1,000 drifters, okay? And add more platforms, because drifters alone are not enough. You need to have, sampling in the ocean, better sampling in the ocean, and other instruments. In particular, we wanted to have aerial observations. We wanted to have 1,000 drifters. We wanted to have aerostat attached to a ship, looking at things, AUVs, towed stuff, whatever you have, we feel is. And in addition, of course, models and satellite data that's always there. Models are not super useful during the experiment, in our experience, but they're very useful gearing up to the experiment. You get a familiarity with the flow field. So the problem is that during the first experiment, we ended up dumping 3 tons of plastic in the ocean. So I felt very guilty about that, because I didn't know plastic was bad for the ocean. This was like a long time ago. And then we said we cannot keep doing that, and more and more drifters and more plastic. So we wanted to develop biodegradable instruments. Okay, so we developed a biodegradable drifter on our own. Also, it was not just the plastic, but the space, because we couldn't fit 1,000 drifters on our ships. And assembly time, it just takes forever, and too many parts and all that stuff. So we ended up developing our own drifter. We tested it in the lab. We have a wave tank, small one, medium-sized one at the University of Miami. So we conducted 1,000 experiments, 10 winds, 10 waves, 10 currents. And this was published, so we know the drift characteristics very, very well. After the experiment, there was a lot of interest in this drifter. So we patented it, and it's now being sold commercially through a drifter company. We have a lot of customers. We can deploy it from the air, and so on and so forth. So if anybody's interested. So this is how the experiment looked like. This time we had 2 ships. Now we are going to deploy 1,000 drifters. This was the first deployment of couple hundred. And this is another deployment. They will run away once in a while because this was a winter experiment. There were a lot of fronts or storms coming in, 6-meter waves, so they couldn't deal with it. These ships couldn't deal with it, so they will run here once in a while. So this kind of like 3 pockets of 300 drifters and some other sampling going on. So they just didn't dare to go out. And then this was nice array drifters. They are still hiding. And one of them will sample, and I'll talk about that. So did we find? So this the whole thing. 4 or 5 months of trajectories. All drifters were deployed in the northern Gulf of Mexico. We kind of filled up the whole basin. Yeah, by the way, this is Miami, this is Florida, Gulf of Mexico. I didn't describe that, but this is Europe. So, did we find anything interesting? Yes, I would say. So we deployed 300 drifters over 30 kilometers by 30 kilometers, and after a week, they will all collapse on a dot. Okay. So this is a 1 million times reduction in area. Okay, I'll show you once more. This is kind of a regular pattern. It didn't work quite well in this experiment, but some are leaking out. But then you see there's something going on here, and they just go on a little area. Actually, we went there with the ship, and they're all there. It was fascinating. So this was a deployment intentionally. It was not a random deployment. We actually looked at satellite models before. There was a kind of a submesoscale-ish type of front developing, and we targeted this front. This is the aerial vision. I'm going to talk about that. And then once this thing rolled up, Eric Dassaro deployed his floats and measured the vertical velocities of a couple of centimeters per second, which is very, very high for the ocean. So we thought this was kind of so this is collapse of from the size of a large city to size of this campus, kind of even smaller than that. In a few days. And then we thought this was a kind of a very special event, but now we have the all data sets and a lot of students are looking at it. The data is full of these things. I'll just show you one more, but you know, I have dozens of these things, okay? You see, just look at how good we got at some point, you know, perfect. This is all deployed from, you know, ship, not a model. And you see they will all collapse on lines or sometimes points like the ones before. So the only thing you need to be able to observe these things is a lot of drifters. Okay, if you have 2 drifters, you will not see that. If you have a couple hundred, then you start seeing these things. It's like a digital camera. George was talking about that. You know, a few pixels, you cannot see it. If you have very high resolution, then you start seeing all the details. So from that point on, fronts really got our attention. And we wanted to have a way of kind of seeing the fronts around the ship. And we worked with some German colleagues to have a marine radar, high-resolution marine radar installed at the ship. So this is the ship. And so we had the screen over there. And this thing would see all the fronts. It worked very well for the fronts around the ship, up to about 3 kilometers away. And it also calculates the velocity field. So this is the track of the ship. And all these vectors are derived from the radar, and we made a comparison with the drifters, and there's a very good agreement. Unfortunately, this is not real time, so you have to do it afterwards. It takes a student a couple months, but this thing is real time. So you know where you are with respect to the front, and that really helps with, you know, precise targeting. We had a lot of airplane operations. We had 200 hours over flight time over our experiments. So we got this plane, made a hole at the bottom, and put 3 cameras. One is for temperature, and the others are for visible roughness. And then, you know, this is essentially the other side of the hole. It would feed into a laptop, and we would be able to see what's underneath in real time from the laptop. Okay, and then guide the fly the plane accordingly. So this is what the laptop shows. It's a real thing. It's accelerated a little bit. And then we would see, okay, what's going on? Is there anything interesting in this particular front? And then there seems to be a front here, and we are now talking. I flew this many times. I mean, I spent a lot of hours in the plane. So now we told the pilot, hey, you go around and make a pattern over it. Okay? So the plane would fly a 10 kilometer by 10 kilometer pattern. That takes about 2 hours. And then we would stitch these things in real time. You know, by the time the plane was over flying this thing, we would have one image that's 10 kilometers by 10 kilometers. And here you see, you know, ADs of few kilometers in diameter, a front. You see multiple fronts. Okay, so there's stuff in the ocean that's submesoscale. And then we would find the ship in the ocean that's kind of waiting for the image. And we would transmit this image to the ship. And they will know where they are with respect to the front. And then design a sampling pattern around this. Okay, because otherwise from the ship you don't see anything. You just, it's blue. Yeah. And this is of course much better than having satellite image. You know, sometimes you have clouds. We would fly below the cloud top, cloud bottom, and of course very, very fast. But this doesn't give you necessarily velocity field. So in order to compute a very high resolution velocity field, we decided to mimic the laboratory technique called PIV, in which you release a bunch of particles and then you sample the particles, and then from the movement you can actually compute the velocity field. For that we needed to, you know, fly a camera at the surface, you know, to look at the surface of the ocean. So we got the highest resolution camera we can at that time. This is a couple of years old already. And of course we need to know where this instrument is. Okay, because again, in the ocean, it's just you don't have a reference point. So there's some devices to know where this is with high accuracy. This ended up being a pretty heavy package. So we bought a big balloon, 5 meters in diameter. It's like pretty big. You need a lot of people to pull it down to test. And then we attached it to the plane, to the ship, to one of the ships. And this is a FAA regulated height. You cannot go higher than that. And then this would take images every 15 seconds for 4 hours. And then we bring it back, get the data, change the battery, send it up for another 4 hours. And it looks at this bunch of drift cards. These are, of course, biodegradable. Bamboo drift cards. Very careful about it afterwards. And this is one of the images. So one image would look like this. We actually have the cards painted with biodegradable water-based. I feel so bad for all the animals. So we would deploy these things, hundreds of these things, and take the images. And then the challenge became, how do you distinguish this from, sun glint? This is probably sun glint. So we had a very talented guy working on these things. Did it work? Yes, it worked very well. So we have this now, the plates all isolated. The movement is precisely determined, and this is their motion is plotted every few minutes here. And then from there we can actually calculate velocity field, surface velocity field, and compare to models of Langmuir turbulence and things like that. Tom mentioned that we should have a part about the scientific outreach, applications, social impacts, that kind of thing. So one of our more applied type of cruises was to look at the longest oil spill in the Gulf. It's been going on since 2004. When a hurricane hit one of the drilling stations, knocked it out, the company kind of went bankrupt, but they still have quite a bit of money they don't want to give. So they have been kind of resisting, in particular saying there is no oil spill. And then the Coast Guard was saying, oh, we are not sure if there's an oil spill because it's not affecting the coast. So it's a very suspicious situation. So they don't quite even tell you the location. So we just went there looking for it. And then when we got close, we had to wear masks. Okay, so there's an oil spill. And we had also, again, SAR images showing clearly there's an oil spill. And the funny thing is that here, So the oil spill is right here, okay, just very close to the coast, but it doesn't go here. Why? Because it is completely blocked by the Mississippi River freshwater transport barrier. So this is essentially image we took. On one side is ocean water, on the other side is the river water, and the oil is essentially at the interface. And we released some drifters and found out that some of it goes to Florida, some of it goes to Texas, nothing of it goes here. Some of it is the tiger tail type of thing. So this is one of the reasons why it has been kind of hiding in plain sight. And then one of the, this was published, and one of the co-authors dared to take on the oil company and go to Washington Post. Got a lot of publicity, which then attracted the attention of the Coast Guard. And now the Coast Guard said, you know, if you don't fix it, you are going to pay a huge fine, and we are going to fix it. So there's some movement to close it off. And the estimates are, if it's not closed, it can leak for 100 years. We were involved in a direct response of an oil spill, and you know, I was flying from US to Europe, and just that day, I got a phone call saying that, oh, you know, why don't you, there's an oil spill, why don't you deploy your drifters? And so these things are really like very hectic, you know, you have to act like in hours. So first of all, we didn't know where it was. That's usually secret. There's an oil spill, but we don't know where it is. It's hard. And then we don't know how close you can get and things like that. So we designed very quickly just a deployment scheme based on various distances we would be allowed to get close. Finally got the location, and then our ship was getting closer, was turned back by the Coast Guard, and we settled on one of the, I wasn't there, but my students settled on one of the deployment patterns. So the ship is coming, we deployed a bunch of drifters, and we gave these maps to NOAA and the Coast Guard in real time. So the dark area is the area enclosed by the drifters instantaneously. The pink area is all the areas that were kind of visited by the drifters, possible pollution area. This is the center of mass. And then what's interesting to me in this exercise was that there was a small eddy offshore, and it fell in between satellite tracks, and it was not assimilated in models. So the models completely missed this stretching that's happening by this eddy. And then we gave these things to biologists and chemists, and they actually use these maps to kind of guide their sampling of damage. And this was published a couple years ago. So oil spills are, they don't happen every day. They happen maybe every 10 years, 20 years. Big ones happen, hopefully never. And when you do experiments away from, people, it's very difficult to convince them that you are doing something. They don't see you, out of sight, out of mind kind of situation. So we said, why don't we, look at problems that are important for most people? For instance, Miami has a nuclear reactor that's kind of leaking slowly into the ocean, and we have a big port. Ships are coming, and sewage is a big problem because most people don't know that Miami is here, and then there's a kind of big bay here, which is very, very shallow, 2 meters, and a lot of the sewage of Miami leaks into this before going into the ocean. So this place is very prone to pollution. So we said, okay, our instruments, very compact drifters, can be used in these areas. These are not massive, big ocean instruments. You can deploy them. In fact, kids can deploy them. So we had a lot of high school kids deploying them over time. So like every week there was a group go out and deploy these things. And then when they start seeing all these complicated trajectories, of course, it's a very complicated place. A lot of islands and all that stuff. This is actually the highest, the richest island in the United States, and it says apparently a lot of pollution around it. So that's one of the major findings. So they were in the newspaper and so on and so on. So we made an outreach event out of that for a long time. This is added because of the last talk. I became very worried about plastic pollution, and we wanted to know, what's the surface velocity field where most of these microplastics tend to be. So we combined a lot of our instruments, plates, drifters, radar, and we had a lot of instruments mounted in the front of the ship looking at wave slope and things like that, polarimetric cameras. And then we're able to obtain a profile, velocity profile, all the way to 1 centimeter. because when you talk about surface velocity field, people talk about 10 meter, 1 meter. It's hard to get to 1 centimeter because this thing is moving up and down. And we found that the surface, at 1 centimeter, the speed is 4 times faster than at 10 meters. So it's a big difference. All the Stokes and all that. So we started making videos, and the reason for that is my mother was asking, could you please tell me about the project you're working on? And I would give one of those PowerPoint presentations, and she would be like, okay. Not impressed. Somebody said, why don't you make like short films, 2-minute films or 4-minute films? So we started making these films. And we had people to make these films. It cannot be like 1 hour or 2 minutes. And then the way we could reach a lot of people was to enter in competitions. There are US-wide competitions where if you have a published paper, you can submit this movie. And it's reviewed by 30,000 high school or middle school students. And they rate it, and then the winner gets $1,000. But it's more like accessing all these people. So we won the last 2. That was probably our biggest impact. And then we had an outreach person having a lot of fun. I didn't participate in most of these things. So, to summarize, yes, in our view, submesoscales exist in the ocean. They are very, very fast. I mean, not days, hours, okay? And they are, because of this very, very dynamic nature of these creatures, you need new types of instruments, fast instruments. And the preferred way is to use aerial instruments to detect these things, and then put a lot of drifters, large numbers of drifters, to track them in real time. We didn't find all that much seasonality in the Gulf of Mexico because, unlike the Atlantic, where you had this mixed layer deepening, most of the submesoscale motion in the Gulf of Mexico appears to be associated with freshwater outflows. So those are the ones creating the buoyancy gradients. The main job of the submesoscales, so they are not geostrophic, they create huge amount of horizontal convergence, order of 10 F. I mean, the estimates, it gets very difficult to compute that when the drifters are getting close to one another. Well, 10 F, 20 F, 30 F, I mean, some people are estimating 80 F in our group. If you think about Langmuir circulations are 300 F, okay? Geostrophy is 0 F. So they collect a lot of the material in these frontal zones, and then as the scales get smaller, we have papers showing that the convergence rates gets higher. So you should not forget about small scale vehicles because they are the ones compressing things. And associated with these convergence zones are high vertical velocities, very high for the ocean. If you think of thermohaline circulation, vertical velocities will be 10 to the minus 6, 10 to the minus 7 meters per second. So this is like 10 to the minus 2, something like 10 to the minus 2, maybe higher, because we don't quite even have the instruments for that. And therefore, the notion we have now is that you have these submesoscales collecting material. There is probably 3-dimensional turbulence there, and they are the conduits to the 3-dimensional circulations. It's shoot things down, and this is one of the focuses of a couple of people here in this same project, Calypso, where we are trying to understand the 3-dimensional circulation. And finally, DARPA, they're kind of a very secret agency. They have been kind of following our activities. And they like this idea that inexpensive, huge numbers of sensor arrays monitoring the ocean. I mean, they want to put cameras and acoustic sensors, 5, 6, and not just position. They don't actually care about position as long as they kind of homogeneously sample the field. And they have now a program, I'm in it a little bit, not too much, to have 50 sensors, 50,000, sorry, not 50, 50,000 sensors that they want to keep, maintain in certain regions of the world. With that, I would like to thank for your time, and in particular the organizers for inviting me here. Questions?
Okay, thank you very much. Other questions?
Yeah. Oh, Nadia.
Tamay, fantastic.
Oh, come on.
This is
Italian.
a great thing. So I see that you don't use tethered instruments. We do use a scanfish, for example,
We had
to sample very rapidly in a very small region.
We have it.
You did?
Yeah.
But
I
you
didn't
didn't show the structure in a vertical.
Yeah,
or the
we had.
How is it?
We had a Remus type of. It's the same as scansh. We were running it the whole time during the experiment. Yeah, up and down.
But this is a good instrument.
Very good instrument. Yeah. It's a it's on CTD.
So not only drifter. I would say
Not only drifters.
we need to get the
Yeah. I agree completely. Not the CTD cast, but the
scanfish.
yeah. Yes.
Excuse me, it's a very naive question because I'm not a specialist. In principle, the ability for a particle to follow a flow depends on its density with respect to the flow. So can you play with this kind of things, with density with respect to the flow, to scan rather vortices or in between vortices or not?
I mean, Lagrangian particle is this esoteric thing. It has no mass. It's infinitely small, and we know everything about it somehow. And and we actually made our drifters smaller because of that. But so my ideal thing would be something completely biodegradable, something like seagrass or something. Maybe one of her particles that's infinitely small. I mean, even at your level, you see differences. Okay, so this is the best we can do for now. But of course, the question of the buoyancy, these are positively buoyant, mass, etc., those are challenges. That's another grand challenge, I would say. If you want to seed millions, I mean, where we are coming from, mullers seed millions of particles in the flow field at each time. And we are now 1,000, the big clumpy things in the ocean environment. So there's still a big difference.
Tamay, thank you, first of all. I have a naive question that links a little bit to Nadia's. So these are these vortices that are presumably somewhat coherent in a vertical. And if in a Lagrangian context, you'd like to probe the vertical structure of these motions, then is your only option those Lagrangian flows that are used by the APL group? Yeah. And so then would you still, if you wanted to get enough confidence in measuring that structure, you would need also a very high number of those, I assume, or you could get by with a little less?
That's right.
Okay.
So we have 2 typically per cruise. I mean, this Eric Dasaro's floats, and so this a bit in discussion. So they cost $300,000. So
okay.
It's all. I mean, I liked Matthew's approach of going towards cheap, inexpensive large number. That's the way to go. Inexpensive large number of sampling, not the glider. I hate the glider.
Okay.
Because it says $1 million and it does something here. It doesn't give you a lot of information, in my view. Yeah.
Okay. Thank you.
All right.
Another question?
I did really enjoy your talk, and just following up on Nadia's question, there are lots of efforts by ONR and others to use this in combination with ships. So don't give ships too hard a time with the profiling CTD instruments. Those are really crucial for understanding the dynamics. But my question was, especially in this context of the DARPA project, where you're actually trying to keep things homogenized. So obviously you have this massive collapse, onto these points and lines. So my question is, what's the time scale that you observe them to subsequently disperse again from those?
This is a very good question. So we are actually looking. I don't have an answer for you yet. And in particular, so our suspicion was they would disperse off, when the winds pick up. But somehow we don't necessarily see that correlation yet, so that remains so I mean, you have this fronts, I mean, the isopycnals cropping out to the surface, and then how is it that you detach from that? So wind is an obvious thing, waves are an obvious thing, but we don't quite know how that happens. Yeah, that's a very good question.
Thanks for the great talk. I was intrigued by your point attractors that you showed for I think you call them the point sinks.
Yeah.
And was there, the reason I'm asking, if you did further analysis on that, a few years ago, we wrote a paper exactly on these things. So,
Okay.
and there was a mathematical theorem there that says that as long as the motion of these drifters or tracers is governed by a Maxi-Riley type equation, you know, in rotating frames, then you can get exactly that point attractor, and it's nothing else but the local maximum of the Lagrangian average vorticity deviation. We did simulations that showed this amazing collapse of inertial particles on these, and we had never known before what these points are. And right now we think we know. So I find it fascinating that there's an opportunity here to check that out. And was there actually something conclusive on locating these, or in the sense, can you predict them solely from the velocity field, or because you mentioned the student was working on them? Because if not, then I'd love to look at that data.
No, I don't think that we can predict them. We are not even close to.
Right.
I mean, we were lucky to have found one of those, but no, prediction
That's
is prediction of fronts, all that kind of stuff. Is everybody is like wants to predict them because they kind of affect the oil dispersion a lot. I mean, if you look at this picture, right? You can easily say, okay, could be a lot of reasons, but okay, these are submesoscales, and all of the oil is concentrated in these fronts. So they collect all of the oil, almost all of the oil is concentrated. So I want to predict those.
Right. I mean, I think to us, those are clear at our level. They are transport barriers, or if you want, they are unstable manifolds. We can predict them from velocity data.
So we would be very interested in this.
Right. But these point sinks, those were new, and I don't think we've ever checked these results, these exact results on data. So I see here a great opportunity.
I would be very
could
happy
do that.
to share the data.
Okay, excellent. Thank you.
It's not a secret. It's very collaborative.
That was a very interesting talk. I was interested in these buoyancy fronts you have between the fresh and salt water, and whether you had any information about the buoyancy fluxes across those fronts. I mean, you showed temperature data with gradients in temperature.
Yeah.
And I wondered if you...
We have the measurements. I just don't have... I mean, you mean buoyancy fluxes?
Well, just to understand how quickly this mixing occurs across the fronts.
Not that much, because you didn't stay there very long to be able to compute these things, and they morph from one another and all that stuff. It's even I wouldn't even know how to. You have to kind of sit on it, or how would you do this? How would you measure it? I don't know. I mean, we didn't look at necessarily the fluxes. Yes.
One other question. When we do our submesoscales survey, we try.
Yeah.
In a poor man, I'll show something this afternoon. We find a lot of coincidence between submesoscales and near inertial waves. So it's for the time being a coincidence. So do you have any buoy data nearby these
NOAA.
submesoscales?
We have NOAA. You mean wind measurements?
No. Well, I'm talking about subsurface.
Yeah.
And an analysis of currents in the subsurface, a spectral analysis that will show you the peak of near inertial waves for this area in the subsurface.
Yeah.
So the submesoscale are up.
How far down?
The thermocline.
No. We were on the upper tens of meters.
For the buoy, I mean the buoy.
Yeah,
so you normally we now have understood that we need a buoy to stay nearby, keeping the time series.
Okay.
And then out of that, nearby have all the rest of the. But you didn't find any near inertial.
Nothing that I'm keenly aware of.
Okay, fine.
All right. Probably.
Okay. Thank you very much.